All right, everybody, this is chapter 3, section 1. Very important section. It's the foundation of the derivative. It gives you an understanding of where it comes from and a full understanding what the derivative is. Again, I'm going to give you a formula that might be a little confusing, but you need to spend time, wrap your head around it until it makes sense. You don't want this to be something that's, oh well, I don't get it. You need to get this. This is foundational to the whole next two chapters. So what we have here, that black curve you see, is a function. And then, so here, the black curve is the function. The green line here is a secant line. And the red line is a tangent line at this point here. Now, our goal is to find the slope of that red line. Now, from past history, you know that slope is f of b minus f of a over b minus a, rise over run. But you can't find that because we only have 1 point. We don't have 2 points to find a rise and a run for this tangent line. But for this green line, we can. And I'll switch back and forth between this and another picture. But the cool thing, see this second point, I can move that. And as I move this closer and closer to the first point, notice what happens to the green line, the secant line. The secant line gets closer and closer and closer to the tangent line, and it approaches the tangent line. So that's what's going on. So we're going to find the slope of this green line, and then we're going to let the distance from this point to this point get smaller and smaller. That distance will approach 0. In that limit, the slope of the green line approaches the slope of the tangent line, and that's how we're going to find it using limits. So prior to calculus, you could not do this because you needed 2 points to find the slope. But in the limit process, this approaches this point here. It doesn't actually reach it, it approaches it, but we can find what it approaches, and that will be the slope of the red line. That's the kind of the idea of what we're going for here. So we're going to get a random slope of this secant line here, just a random slope, general slope for any secant line. And then we're just going to move this point closer mathematically, analytically, and find the slope of that red line. So let's go to this. So here is the same situation. Colors are different. The function's red instead of green, black. Colors have changed a little bit. But we want to find the slope of this tangent line. So I probably should label that tangent line. We want to find the slope of that thing, okay? The green one is a secant line. I'll label that. And the red function is our function f of x. Okay, so slope is rise over run. So the rise is this distance here. Now we have points a and b, 2 general points. If you plug a into the function, it gives you the y value, which is f of a. If you plug b into the function, it gets you the y value, which is f of b. So we want to find the rise, and that's going to be this distance right here. Well, how do you find the distance between any 2 points? You subtract them. You take the bigger one, f of b, subtract the smaller one, f of a. So that length is f of b. Let me make that fatter. F of b minus f of a. And similarly, we want to find the length of the run, that one. Well, you take the bigger number, b, you subtract the smaller number, a. So that's just going to be b minus a. And so for that green line, the slope is going to be rise over run. And what's the rise? Right here. What's the run? Right here. Should look familiar to you. F of b minus f of a over b minus a. That should look familiar because that is the equation for average rate of change. And we learned that in the last lesson. So average rate of change is the slope of the secant line, And that's what we're looking at. But remember what we did. That was not supposed to happen. Remember what we did. We took this point and we moved it closer and closer and closer and closer to A. And what happened, I'll show you in the video again with the animation. As we move this point closer and closer to A, the slope of the secant line approaches the slope of the tangent line. And that's the process we're going to do. So the first step in this process is recognizing the slope of the secant line is f of b minus f of a over b minus a. So we're going to take the limit as, we'll see here, b approaches a. So here's the average rate of change, the slope of the secant line. That's the formula you should know. This should make sense to you. If it doesn't, you need to wrap your head around it. You need to sit with it until that makes sense. That's the slope of the secant line. So that's what you got to do with that. Then, after you do that, you take the limit. All that's saying is you're taking this and you're letting A or B approach A and get closer and closer, and you know that this slope approaches the slope of the tangent line. So the slope of the tangent line is the slope of the secant line in the limit as B approaches A. This is how you find the slope of the tangent line. We're going to use that for our first example. Find the slope of the tangent line of f of x equals x squared at x equals a. All right, so when we see that, here we go. We do the slope of the tangent line equals the limit as b approaches a. And again, the b and a are, you can use any variables, but that's just what we're using a lot, so we're going to leave it like that. So what's it going to be for us? What is f of x? F of x is x squared. So you take x squared and you plug in b, that's going to be b squared. And you take the function, you plug in a there, you're going to get a squared. Ooh, I forgot my limit. I can save this though. I can save it. The limit as b approaches a. Now from chapter 2, these are polynomials. So to find the limit, you just plug it in. So if you plug in an a right there, you get a squared minus a squared. You plug in a there, you get a minus a. You get 0 over 0, which is indeterminate. Do you guys remember what to do? Hopefully. Do you remember factoring and canceling? So we're going to factor the top to b minus a, b plus a, factor the bottom to b minus a, and beautifully we get it to cancel. And then b is approaching a. If that turns into a, we end up with a plus a or 2a. So the slope of the tangent line is 2 times a. But what is a? It's the x-coordinate where you want the slope. So depending on where you want the slope, if you want the slope at that point, you plug in this a. If you want the slope here, you just plug in whatever the x value is. So understanding this a is the point of tangency, and this is the slope at the point of tangency. So if that made sense to you, awesome. If it didn't, you probably want to re-listen to this and go through it. Very important foundation. All right, what is this? Okay, this one's different, similar. Instead of at a general point A, which could be any point, now we want it specifically at 1. Specifically at 1. So it's going to be the same formula. But now our A is going to be 1. The limit as, I don't want to confuse you. Oh, let me do this. I'm going to use x and 1 instead. As x approaches 1, it could be, again, you could have b here, b and 1. Normally it was b and a, but just to get you comfortable with different variables, we're going to use x and 1. So in this case, the slope between those 2 points is going to be, I didn't want to use that color, f of x minus f of 1 over x minus 1. So in essence, this is exactly the same as that. The only difference, we're going to use x and 1 instead of b and a. But everything else is the same. The b is the first one. The x is the first one. The a is the second one. The 1 is the second one. Same thing. So we're going to go through the same process. We're going to plug x, well, f of x is f of x. That's the original function, x squared. That's easy. Then you're taking the function and plugging in 1. Well, what's 1 squared other than 1 over x minus 1? Well, again, how do you find these limits? You just plug in 1 here, 1 here. You get 0 over 0, which is indeterminate. I almost said L'Hopital's, which is chapter 4. And then we have to do something. We factor and cancel. That goes x minus 1, x plus 1 over x minus 1. And beautifully, they cancel. You take the limit. In a limit, you just plug in 1 here. And 1 plus 1 is 2. So the slope of the tangent line of an x squared, so x squared, remember, kind of looks like that, right? But it hits the 0 mark. At 1, we found the slope of that line is about 2. Now you're going to say, that looks like a 1 slope. Well, my graph's not accurate. If you had an accurate graph, you could see that that slope is going to be 2. But look at the difference. We did the same function, one at a general point A, the other at a specific point 1. Which one is more helpful? I tell you, this is more helpful. Because for this one, you only know the slope at 1 point 1. But this, you can find the slope at any point you want to. And again, let's take a look at this beautiful x squared graph. What if a is 0? What's the slope here? Well, clearly that slope is 0. So you put a 0 here, that's 0. Now, suppose you want to do it at 2. If you plug a 2 in, that's a slope of 4. So when you go over to 2, you know the slope at that point. So this one will give you the slope at any point you want on the curve. This one is limited to that very specific spot. So the general is much more helpful. All right? Now, here's another way to find the slope. We're going to go through the exact same process we just went through, but just with different things. So we're starting at x instead of a. And this time, instead of going to b, we're going to x plus h. But what does that mean? The length of the run is h. So if you start at x, you move over h, you're at x plus h, obviously, right? Therefore, this point, the y value, you just plug x into the function, f of x. And for this point here, the y value, you plug x plus h into the function, x plus h. There's your y coordinate. So we're going to go through the same thing here. What is the run? It's the bigger, or not, excuse me, the rise. It's f of x plus h minus f of x. You're taking the upper point, subtracting the lower point. The bigger number minus the smallest number is the distance. And you can do that here. What's x plus h minus x? It's h. So if we want the slope of the secant line, that's going to be rise over run, right, of this guy. Well, what's the rise? It is f of x plus h minus f of x over h. And again, have that make sense. Don't just like, oh, it's confusing. It's not that hard. Once you see it, it's easy, and then you're not going to forget these formulas we're giving you. You will not forget. So look at that. Make sure that makes sense. Rise, run. If I start at x and at x plus h, the distance between those 2 points is h. You find the y values, the distance you subtract, and you just do rise over run. So that is the slope of the secant line. That's the second formula. Okay, that's the slope of the secant line. But just like before, if we move this point closer and closer, the slope of the secant line approaches the slope of the tangent line. That's our goal, right? So we're going to move this point closer and closer that way. As we do that, what happens to h? H gets smaller and smaller and smaller. So if we can take this slope and let h approach 0, h being the distance between these 2 points, we're doing the same thing. We're sliding along here. H is approaching 0. So there's your second formula. You take the limit as h approaches 0 of the slope of the secant line. This is also average rate of change, just written differently, right? We're introducing this weird variable h. But another formula that you need to know, you'll see this on the AP test. Not very often, but you will see that. So we're going to use this formula now to do the same problem we did earlier. So we're taking this problem that we did with the first definition, and we're going to apply it using the second definition, okay? So find the slope of the tangent line. The slope of the tangent line will be the limit as h approaches 0 of f of x plus h minus f of x over h. Now we're going to plug in our function. What is f? F is x squared. So we're going to put x plus h into x squared. This just takes practice. It gets easier. X plus h into our function x squared. So it's going to be x plus h into our function squared minus f of x is just the original function, x squared, over h. Now in this limit, as h approaches 0, if that becomes 0 and that becomes 0, I get x squared minus x squared, which is 0. So we have 0 over 0, which is, again, a case of indeterminate. What did we do? In general, we factored and canceled, but factoring that, well, it's not always going to be this easy. I'm going to show you the general way. I guess you could do difference of 2 squares there, but I'm going to do it a different way. At the top, I'm going to multiply out. That's going to be x squared plus 2xh plus h squared. I just FOILed that out. Minus x squared all over h. And these will cancel. I'm left with 2xh plus h squared over h. Now, again, if I put a 0 here, a 0 here, a 0 here, that's indeterminate. I need to factor and cancel again. So they have a common factor of h. I take h out. I'm left with that and h on the bottom. So they both have a common factor of h. If I take it out, this will give me 2xh. This will give me h squared, so I know I'm good. And again, magic happens. Those cancel. And when I take the limit, if that approaches 0, we just get 2x. Look at that. So if you want the slope of the tangent at any point x, oh, it's supposed to be a. OMG. I'm not going to redo this, but watch. I planned that because now all you do is replace all the x's with a. A. See? Sorry about that. Same thing. Because x, the point is a, right? So if I want this to be the point of tangency, that has to be a. So that's a plus h. So everything stays the same. Instead of x's, you have a's. So it's 2a, but look what we found up here. Same answer. So we can find the slope of the tangent at any point by plugging in the x-coordinate there. All right, this leads to a definition of derivative. The definition of derivative, it is the slope of the tangent line. Look at that. That little mark there, that means derivatives, little apostrophe. The derivative of a function a is what we just looked at the slope of the tangent line. Those two things. Now, a could be x. It didn't have to be a, but if you did x, it'd be confusing because we have x there. That's why we use a. These variables can be any variable you want to be. So, huge It's crazy. I have people, second semester, I ask, what does the derivative tell you about a graph? And they can't even tell me. I'm going to tell you this so many times. It is essential. You know, the derivative gives you the slope of a tangent line. You saw it from the illustration we have. You're just going to hear it over and over. The derivative is the slope of the tangent line. It's also called the instantaneous rate of change. Instead of average over a period, it's a rate of change at a single point. So that's the symbol for derivative. We also use this notation. We use this notation, this notation. All these are valid notations for derivative that you have to be familiar with. And for the derivative at a specific point, like the derivative at 1, this is the notation using the dy dx, the differential notation. So something you just have to be familiar with and comfortable with. So just be aware of these different forms. Now, we have a couple more problems and we are done with this video. The first one, what is the slope of the tangent line using definition number 2? Definition number 2, the second one we gave you is this. The limit as h approaches 0 of f of x plus h minus f of x over h. We're going to plug in what we know. This one's going to be a little trickier, not as nice as the other one. X plus h, I plug in for each x. So I'm going to get x plus h squared minus 2x plus h. So if I plug this x plus h into all the x's, that gives me f of x plus h. Minus, let me get an extra parenthesis, f of x. So it's just the whole original function. X squared minus 2x all over h. Now as h approaches 0, that'll become 0, that'll become 0, and I get 0 on top, 0 on the bottom, so I need to factor and cancel. This is where it gets a little ugly, a lot of algebra. If I square that, I'm going to get x squared plus 2xh plus h squared. And then if I distribute the minus 2, we get minus 2x minus 2h minus, and I distribute that, I'm going to get x squared plus 2x all over h. I need to simplify. X squared minus x squared, gone. I like that. Minus 2x plus 2x, gone. I like that. And then I didn't give myself space. I'm going to have to come back and erase that. But let me create some space. So that gives me the limit as h approaches 0. On top, I'm left with 2xh plus h squared minus 2h over h. So that, and that. Now, if you plug 0 in here, 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 and here, you get 0 over 0. I need to factor and cancel. So the top, they all have h's, so I'm going to factor that h out. I'm going to be left with 2x plus h minus 2 over h. And again, beautiful canceling. I put a 0 for h. I have 2x minus 2. We have found the derivative or the slope of the tangent line. And I probably shouldn't have said derivative. Find the derivative of. Same thing, but that's what I meant to say there. Okay, one last problem. We're going to be done. Let me erase this here. I erased my problem. That was, whoa, wrong one. I'm having issues here. There we go. This is a very important question. You will see this. You'll probably do this at least 100 times, maybe 200 times this year. It's always on the AP test. Very important concept, the equation of a tangent line. So this is really easy, but people struggle. Again, don't memorize. This makes sense. First, you have to know the point slope form of a line. If you have a line that goes through x1, y1 with a slope of m, here's the equation of the line. You have to know that. Have to know that. You'll be quizzed on it over and over. And again, this is another thing that I'll go through a semester and people still don't know this. That's embarrassing. You got to want it. You got to want to do well. So it's up to you. What is x1, y1? What's the point that this line's going through? It's the point of tangency. It says that x equals 2. So I need f at 2, which would be 2 squared minus 2 times 2, which is 4 minus 4, which is 0. Wow. So my x1, y1 will be 2, 0. 2, 0. Right? So that's the point of tangency. That's my x1, y1. Now I need the slope. What is the slope of the tangent line? Well, it's the derivative. Well, we just found that. The slope of x squared plus 2x minus 2x, we just found that derivative. Oh, and I erased it. Okay. This is coming back to bite me. So f prime of x on the previous one was 2x minus 2. We're going to use our previous answer. The slope of the tangent line is going to be the derivative at 2. Again, why do I plug in 2 here? Don't memorize. This should make sense. That's the point of tangency. That's where I want the slope. Don't memorize. That makes sense. So that's going to be 2 times 2 minus 2. I just plug in 2 into this derivative formula. What's the slope? 0. Wow. So this is going to get pretty easy. Now I plug it into my general form. Y minus y1 equals m, x minus x1. y1 is 0. The slope is 0. That's too easy. I'm sad I gave you this simple one. And x1 is 2. But all said and done, you get y equals 0. I don't like that, but I guess that's the example. I'm wondering if I messed up, but I don't think I messed up. Oh, I think I did mess up. Oh, I did mess up. I did mess up. Okay. Good thing I caught that. No? No. No. I'm good. I didn't mess up. Or did I? Oh, I did. Sorry. Okay. I see my mistake. I knew something was wrong. What's 4 minus 2? Duh. 2. What's the slope? Okay, I got to erase all this. Much better, much better. I'm happier. Slope is 2. x1 is 2. So the slope is 2. Bam. x1 is 2. y1 is 0. Much better. People ask me, do we need to simplify that? That is the answer. If you want to, you could distribute that, but you don't have to. That is the answer. So that is the end of the lesson. Make sure you understand this. That's it. Have a great day.